schedule for tomorrow morning? Or
You mean for your, definable. Right.
For 6? Yeah. It would have to be with 5 for you.
The easiest way I know of saying what it means to be a definable here now is you have a something like this, where the quadratic of the Hardy metric is reduced. Basically, Schmidt's estimate. I don't know how else to say it.
Yeah, so I keep forgetting. It's really
It's really amazing.
so it's saying that when in one of the two, now we know that the different Charles says.
Well, the metric is more than definable, reduced, with respect to a basis. Well, it depends what you mean by definable metric. You gotta be a little careful. If you just mean the metric is definable naively, like the coefficients are definable or whatever, that's not the same.
Okay, but so first we
That was just mean it like lifts upstairs, right?
Think about it this way, like say you just had a family of lattices, like a trivial, like a local system of trivial locally, and you're just varying the metric. You want to ask, what does it mean for that to be a definable family of metrics? It's kind of subtle. It means there's some fixed basis.
yeah, but so that's why you need
Yes.
to say
Can I ask you a question?
Of
Is the
course.
font size big enough?
I can come closer. It's okay.
Well, okay, if you have to come closer, then the question is the font size
Oh,
of the
that was your
board.
question.
Yes. So if you, the answer is I have to come closer
You
to
know what?
the
The
board.
font size is big enough, but with the glare from the light, the blue doesn't show up super well.
So I should use a different pen?
I think
or-
it's the darker marker. Yeah, but the markers we've been having a hard time with.
But anyway, he's trying to use it like stimuli and stuff, but like show in a more human understandable way
so you want to improve this
It wants to reprove Schmidt, basically. But it's a thing. I think it's just something that they're doing it for curves, because they explicitly.
Well, no, but I mean, I guess it's doing for curves, you can say. That's the one.
But also, but the fibers are curves.
Sorry?
They're currently thinking about the
The
fibers.
fibers, well, whatever.
Yeah,
But the base is also a curve. Everything's a curve.
I think so. But I
I
mean,
don't think the base.
Okay, direction is good. That would be nice. Because our proof really was cheating for her.
I mean, it is. I mean, we were already surprised that it was really it's also surprising that no one thought about when you have it too much. The norm asymptotics and stuff, people get. The norm asymptotics,
You mean not the inner products, the norms?
Yeah.
Yes.
You say you can you get?
Yeah, so
Just norms of vectors, not inner products.
like the norm asymptotics. If you have a geometric variation, because for geometric variation, you can think of everything in terms of like logarithms, like cohomology, logarithm,
I
like
still
that. You
don't
can
understand
immediately
what
get.
you're saying. You know, I think you don't have to write this. You can get some sort of asymptotic expansions, but you might need some terms to vanish that aren't so immediately obvious.
You get the weight filtration for that,
Yes, you do.
and by like I don't know, understanding what logarithmic means. Maybe not. I don't know.
No, like we realized for a long time that Schmidt, we tried to reprove Schmidt by saying that you have some expansions, some polynomial expansion. All you need is some things to vanish, some terms, finitely many terms to vanish, and that's just algebra. We had that,
Yeah.
and we couldn't get it from that.
But that's for wait, sorry, for the
The
norms.
same,
or
it
for
doesn't
the-
matter.
No, but I think the norms are a lot easier.
Maybe. I believe the norms are easier.
Yeah.
Yes. It is. No, so it's very possible. Okay, fine. Norms are easier. But the inner products are hard. I don't know much about it. I I mean, first of all, I don't know if everyone understood Schmidt did it. Section 9 is like insanely hard
Oh,
to
yeah,
understand.
I mean, that's a reasonable
Secondly,
explanation for why no, card.
I don't know how we, I mean, I'm sure there is a proof by Schmidt's style, but why are we really tricky?
To prove what? What do you want to
I
prove?
mean, in any setting, like our proof in higher dimensional case is like, take Schmidt, do the stupid interpolation thing, conclude it for the higher dimensional cases, right? It's like a stupid proof.
I mean,
Pushes it all to Schmidt.
It pushes it all to Schmidt and it does this crazy, I mean, it's a little, I guess it's neat, but like, it's clearly the wrong proof or something. Like, you could be able to directly look at the differential equation.
I think the thing that you're missing,
Yeah, so, I mean, because the reason I think the Norman methodology should be reasonably demonstrated, is because the wave filtration is just interpreted as like the polar order filtration.
I don't know exactly what you're talking about, but I'm gonna tell you something that you really need to be careful with, which is integrability. You really have to be careful with, okay? So that's like much harder in two variables.
Integrability of what?
Of the period map, right? I mean, the fact that N1 commutes with N2, you like, the two monitor logarithms have to commute. If you don't use that, you're not gonna get a proof. So I think you really, somewhere in your proof, like, that has to be built in, otherwise it's not gonna work. So, I'm not following your conversation clearly enough to understand that.
That's all right.
I'm just saying, there is something which, you know, is not just gonna fall out of like, I thought about it for a while. Okay.
But yeah, anyways, maybe, okay. But I don't understand, he's trying to use this, how's he gonna get any control on the inner part? I don't understand.
Well, I don't know, yeah, I don't know.
How would you get
That's why I
rid
was
of
interested.
just a definability state?
Well, it's like looking at these, it's like looking at these annuli, looking at their degenerations, because you're using these like plumbing coordinates and like to precisely understand how that curve is degenerating.
Okay, it's mostly in technical theory, not using definability.
Well, yeah, it's using explicitly for curves, using these explicit coordinates to try to understand.
Yeah, maybe, I never understood this.
Variation of
Don't worry, don't be scared about this.
Hence
It's
diagrams.
very convenient, yeah.
For curve, I think
I
much
actually
more.
needed
Because we
stuff
never really
earlier in the
stuff
week.
we needed.
Earlier in the week, I was busy doing stuff in Beersheba.
Yeah.
Teaching in meetings. Yeah, even though we canceled the summit, I'm not sure if the Gross Lagia seminar.
But yeah, I mean, it might be more, I mean, for curves, again,
Okay,
you
so
have
the Gross Lagia seminar, I haven't been following that as much.
They may be even higher.
It's interesting to me, but there's too much going on.
Even if it is a way
Well, they can't
even
really
if it is a way 100.
Are you talking about campus?
I get a lot of very fine control, I don't know.
So that's stuff I might want to work on.
So don't worry about what's in the
How are you?
So, unfortunately, I couldn't come to the beginning of the week, which is actually what I needed more.
Somebody asked me to show them the example.
Kind of, I'm faculty at Beersheba now.
Cleverly hide the example.
So, yeah, where are you supposed to work? I've been meaning to learn more about lunch theory because of my
I can do that. So that
I
was
guess Nathan Dover and Daniel Hast have been using it
Not
so
to
many.
show that.
You got hot. Yeah, no, I think people haven't explored the
Not to show that.
Hodge theory relation, except for BKM and now.
You mean complex Hodge theory?
Yeah.
I don't understand that.
The only paper I know that
So I'm
does
not,
that
I'm
is
not
like
actually
critics, so.
directly solving the equation.
You mean the geometric quadratic Stiglitz? So I mean, Alex Betts told me at one point that he figured out how to do an Archimedean version of the quadratic Stiglitz.
Which will mean
So he just like means to write it up at some point.
What would it be?
finally get, I can,
So here's the thing, in a Bielic Chevrolet, it's trivial.
I can make.
Because what happens is you mark out, what you do is you modify all of the, you take the complex points of the, from the group, you modify by the real points. This is sort of the key.
Okay, but now here's the thing I need to use, so I.
No, I'm just whatever, take the from the group up to stage N.
Fact.
We can think about a beating or is it fail for it?
Sorry?
Can you just think about the beating one or is it fail?
This is, so the point is what happens is you get
Yeah.
something trivial for you.
Cool.
Well, like not, you'll learn
Integrally.
Exactly.
except the closure.
You have like a family and.
Oh, but you're
No, it's
saying
because
that
the
Formal.
F1 or F0 for the Hodge filtration, together with real points, generate the whole thing.
I see.
That's the key.
Yes, sure.
That's the
I think that's a cool way of doing everything. Yeah, okay, I understand.
That's the least how I.
And you're saying in the uniform case, the stuff being the
In a
case.
paper which is.
Exactly.
That's a good point, that's a good observation.
And the other nice thing is that when you modify all, like, there was this whole question about, well, you have to modify the Z points, in order to.
Yeah.
Just modify all the R points.
Yeah,
Which sounds
you're not,
terrible.
you're not using
Well,
that
no,
to
you know
solve
what you
that,
mean.
whatever
Makes sense.
differential equation.
Yeah, and so then when you do it over, you don't really have an analog of that over 2P. So you take the complex points and you modify the real points. Sure. And then you modify F0, and the point is that when you go up the uniform tower, it becomes bigger and bigger. Whereas the Booleanization, it is trivial. That is the, that's what it seems like that is the perfect and it's like, oh. It's a question of like, the views about Hodge,
I'm not necessarily saying my theorem, I'm just saying, I don't know, there's a general, like, thing in the air maybe, doesn't have to be about, the real gold mine here, if you can figure out how to do any kind of arithmetic for discrete domains so that you get some uniformity, arithmetic. You can have all those algebraic guys, what's the point of the period? The point is to hold all these different algebraic guys together. So you want to make uniform arguments using that. It has no algebraic structure, which means you can't do anything about it periodically, which means all this stuff kind of fails.
Did you see this preprint of mine and Alex Betts and this other guy? It's, you know, like the Coleman bound, the Shepard Coleman bound, and then there was this bound by Ballers and Dobra. So then we basically, assuming Loch-Kato conjectures, include a general bound for all Kraepelin curves.
Oh, that's nice.
So and it looks like a very, much more complicated version of the original Shepard Coleman, the Coleman bound. So it's like, I think at the end of the day, what it's really all about is its bounding sizes of these Galois homology groups. And one of the problems, of course, is that you don't have, like for the p-adic version, right, you have Galois homology, but you don't have a good Euclidean version of Loch-Kato groups. Which is something that I often like to bring up.
Why should I have somebody in the back?
And sort of choose each prime L. So you can't do Loch-Kato groups. Like you do something like a cohomology. A group.
At the moment,
Yeah.
You get information. And then that's
do you
sort of
think there's
what
an
about
unsolvable problem hiding in the classification of surfaces?
Oh,
I mean, there isn't
the point is that if you
really a classification of
p-adically, if
surfaces,
you
right?
cut
There
down
are a lot of
your solid
things that are very difficult. The question is, is
you're
there
expected to get something
any
that has the exact
problem
same
hiding
dimensions
somewhere
as
there
the
which is
corresponding,
really
like,
fundamentally unsolvable?
generalization of this whole, BSD, p-adic, somewhere
You mean,
the rank.
like, does there exist a cardinal between Alex or one kind of like?
Well, I'm more thinking along the lines of,
What are your
finitely, I mean, for example,
Well, just in the fact, in the fact that, to define the Loch-Kato
fundamental groups of manifolds
Oh,
in
so what is
general
tropes?
are all, topological manifolds, are all finitely presented, let's say,
But it's in
finitely
its
presented groups, and we can't classify finitely
Yeah,
presented
that's
groups.
stuff.
Can't even tell if two of them are the same, right?
Well, I mean,
Isomorphism problem, it's not solvable.
I haven't.
It's very,
I never thought of effective stuff, learned that, so who knows? Maybe I'll look at this a little bit for this weird stuff.
The last thing you knew, I mean,
Yes.
wide open, this is wide open, right? And the problem is that
So yeah, there's some triggers that
you're residually finite.
I mean, so what is learned?
This
Work with them on the
I'm curious actually, so you have these things about variation
I
plus
can envision
structures.
something like
Are there similar things about variation, p-adic variations plus structures?
Definability thing you mean?
No,
Yeah.
fundamental groups of
Not
varieties
really,
are
because we don't really have a good definability of it. Yeah, like, we thought about it a bit, you potentially could map
So
it
the
these,
question is, could you formulate something in terms of
these,
theory of surfaces which would boil down to some
they're
undecidable
weird,
problem?
right? Because you want to make it a group.
I've never seen anybody do anything.
But,
It's like the natural.
It's a natural thing to do, so you put that there, and then you could ask for that to be, like, you could make sense of that. At least in the compact case, like separate little capital or whatever. But we haven't really gone on to that very much.
The last
like direct, you've had applications that are much more interesting.
Like, I wonder, so an interesting correctly is like the way that people use a relationship with time is they basically,
Okay, but I don't think there's anything there that's officially known to be
see
illegal.
power series.
Yeah.
That's basically what they do.
Other things related to,
But like, it would be interesting if you just would be directly like that, so.
Yeah.
and you've never heard anybody, right? I mean, the usual, it's clearly a difficult field, right, but the usual
But yeah,
difficulties
you kind of
are
like,
computational rather than
I don't know, some sort of arithmetic.
not presented as an algorithmic.
If you have real primes, you can formally multiply them. Formally
Or I'm
multiply
asking
them. It doesn't move at all.
When you say close to the higher state of definition, it's pure use arithmetic, it means we'll bring up the right.
I just mean like, how about this, it means something for a prime, and glued together.
You mean for different primes?
Maybe after this.
Yeah.
I mean, the thing is, you have the same.
Okay.
Well, here's the thing. The local period domain is essentially this group of homogeneous homogeneous space and the group homogeneous space.
Right.
If you can define that over rationals.
Yeah, there's no decision.
So that's the kind of thing.
No, yeah.
Conjecture.
This is a prime on GZ.
Actually, I mean, okay, so suppose you have
The what? A buffer.
two candidate periods, which you figure.
Oh, you mean in the
So
Archimedes?
you could start, I mean, it's a conjecture, it's true, you can start searching for the of all, different ways of deriving one individual. But if the two things are
The Chevrolet
So going back to
equal,
the rationals.
then you'll be able to, if they're not equal, you can just prove it by computation, right? So because assuming that conjecture is true, you have a decision, the decision algorithm. So you can say that the conjecture is that
Even the localization
it is a decision.
is a map of finite dimensional algebraic representation. Which seems really strange, but this is all just
Yeah, I mean, that's,
Isha mind from like 2019.
I don't think anybody has any,
And then it's
I mean, if you were talking about unsolvability, what you would
into actual data.
need is you need to have on occasion things which are
Sort of the map from the
equal for mysterious reasons, right? Reasons beyond the familiar. I don't think anybody actually thinks that that's consecutive conjecture, you might just say, I haven't proven it. But I don't think anybody has any idea for why mysterious identity can happen.
localization map itself we find over here.
what is KSEA?
Hold on. I will not comment on that.
Yes, the first one, I think it's a number you formally incorrectly.
It's sort of cool now. Part of it is just
Sure. Yeah, so go on and find some sort of height directly.
That's for one, 760.
Instead of that, you can
Okay, no,
No, sorry, send me a message.
and the second,
do that, you need to
let's try to find you.
do somehow. Anyway, yeah, maybe.
Here's second.
I don't, I mean, I really wouldn't put out a shape. The main thing I need to know is like extending to beyond the graph.
Second.
Yeah, under the signature was the whole question about lights. Right. Also, like in a homotopian structure.
So-
How do I block?
And the second thing is,
Arguably, it's a generalization of the way you put the weak word already. For the one
What
here
happens
is
to that?
heights plus the weak word. If you can mix homotopy theory and heights,
like you or, I don't know, how much is supposed to be?
logical sense. The appropriate abstract setting for heights. You have a notion of which subsets are
Right.
focus to somehow mix these sort of more fundamental groups in the higher.
Like 30 and,
Yeah,
it says time. It says time because it's straight from the hotel to the train station.
Direct back to Toronto.
Oh, and the third thing
Yes, exactly.
is, I went outside to look at the phone, and I tried to follow you and
They did.
because I want to talk to you about this thing.
Yeah.
And
Yeah, send me the paper, man.
yeah, how I thought that you entered the library, so I tried to enter, and then I saw you are not there, so I stayed outside and breathed some air.
Oh, sorry, I didn't
Now I
realize.
see you here,
Yeah, sorry, we didn't realize it was behind us. We went.
so I wonder how did you teleport here?
But you don't know the underground tunnels?
Oh, in the cotton. Okay, so don't tell.
That's what it was. Yeah. There was something that went to something that. Yeah. Okay. So I didn't know what. I didn't know.
So I'm not trying to check us. Okay. Fair. For
Yeah, okay, so
unlimited
that's what it
books.
was.
And it should be unlimited books first. Ah, yeah. Like the average user. No, that's okay. So it's 6:30.
Yeah. No. Exactly.
By the way, what can I do here about?
Alright. Some of them are like terrible.
You start early.
Oh, wait. A few others are slightly less scary. I think it was the one in Barbados. It was really just like the like the like if I heard that.
Yeah, I sit down and I take this one sing here.
For real? 2006 we had a few. Yeah, I know. 2006 we had quite a few.
But you got stuck, I'm not just.
Never really understood that general. I've discussed it with someone.
אם אתה רוצה לדבר, זה מתחיל 6:30.
מה זה בדיוק?
announcement. Sure. Announcement?
So Chris Doe is, so Chris Doe is not here because he has COVID and had to stay in UK, but he will give a talk tomorrow. It will be by Zoom, but because of the time zone difference, we will switch his talk and mine. Okay, so we will update it in the schedule, but Chris will speak online in my slot and I will speak in his slot. Okay, that's it.
Okay, for the last lecture today, I'm pleasure to introduce Gregory Perlstein, who will speak about unimodal singularity and boundary divisors in the KSBA moduli space of the class of, I do not know the name, sorry, surfaces.
Classic Okay. Thank you. All right, is it working now? Okay. So first, let me thank the organizers for this lovely conference. I've definitely learned a lot. So thank you for your hospitality again. Okay, so this is joint work with Patricia Geraldo, Luca Schaffler, and Jing Zhang. So I guess in the Sermon's talk today, he touched briefly on this idea that you could resolve this conjecture of Griffiths on the algebraicity of the image of the period map using some type of O-minimal version of the Gaga theorem. Okay, so that's, and I should say that, I mean, that's Zimmerman, Brunebauer, and Bakker, yes? I think I have the attributions, is that correct? And another thing that he talked about a little bit is one component of this kind of, or one input to this kind of O minimal arch theory is, well, you need, I guess, the nilpotent orbit theorem, nilpotent orbit theorem of Wilfried Schmidt, and also his SL2 orbit theorems. So this you need in one variable. And then you also need some norm estimates in several variables. And for the norm estimates in several variables, you can either use a result of Catani, Kaplan, and Schmidt, who are also the authors of, Catani, Kaplan, and Schmidt, or you can use a result of Kashiwara. So there are different ways to get this part, and Schmidt is responsible for that first part. And now one thing I guess I would kind of like to say, so this is the dome right there. So this was kind of an old dream of Griffiths. And that's that you should compactify this period domain quotient. So for me, gamma is usually the monodromy group. It could be much smaller than the GZ that appeared in the earlier talks, but you should compactify this by adding these nilpotent orbits as boundary strata. And so what this would be is this would be kind of a generalization if you know this theory. So first we have this kind of Bailey-Borel compactification, and then Ashmont, Rapport, and Tai constructed this toroidal resolution. And this theory, this idea of Griffiths, would be if you could do this, you would get an analog of that construction for much more general period domains. And so there's good news and bad news about that. So in the 2000s, Kato, Asui, and later Nakayama they more or less managed to fulfill this dream with one important caveat, and this is kind of subject to existence of a suitable fan. Now, in general, they did not prove the existence of a suitable fan except in some very special cases. For example, if you want to compactify the bases of a curve, then you can do it because you can just use one-dimensional cones, and one-dimensional cones, they either intersect or they don't. So this is not going to be a problem with one dimensions, but in general, they didn't really succeed in doing this as far as I know. Okay, but if you could do this, then I will give an example. So this would be for this. This is Kolar, Shepard, Baron, Alexeyev for these KSB8 moduli spaces of general type. What did Asui prove? So this is 2006. This is general algebraic geometry. So that says that if we assume the existence of a suitable fan, then there exists an extended period map phi from, okay, you may have to take your moduli space and play a few little games with it, which I'm not going to do. So gamma is the monodromy group. D was your original period domain, and now you have to add on a bunch of boundary strata corresponding to the span of nilpotent orbits, and for which the image is the analytic space associated to a separated compact algebraic space. So this theory is very different than the definable ones. So the idea here is they actually work in this kind of category of like logarithmic manifolds, and these are also kind of nasty, but the idea is you construct the period map into these things and you have to show that the image doesn't go to, like, to these nasty points. So, but if you could get a fan, then this would give you another type of algebraicity result. And so I'm going to mention that because there was some recent progress by a student of Matt Kerr. So this is 2021. This is Hao Ding. And so he constructed a suitable fan for a class of, let me say it this way, for a period map phi from S into gamma mod D, where here D corresponds to a period domain with Hodge numbers 1, 2, 2, and 2. Okay, so this is an example of how one could do this. Again, so constructing this fan is very, very hard, because what he had to do was he had to take these particular monodromy elements, which are generating this cone, and he had to look at all of their orbits under this monodromy group gamma, and then he had to pass to a finite finite index subgroup of this, so that everything would, so this is like a non-trivial construction what he did here. Okay, and so now, since I think spent a lot of time in the evenings this week, maybe rewriting this talk, so this is like the first time I give this version of the talk. Usually the audience is a bunch of people who are very high-powered moduli theory, so I've tried to strip that all away, so I hope this talk goes okay. So I'm going to start off with something, this is some older work that I did with Matt Kerr and Colleen Robles. And this is about polarized relations. So if you'd like, this is motivation for why I'm going to study the particular problem I'm going to study later on. So again, D is our classifying space of pure hot structures. GR is connected component of the identity in aught R of the polarization. So connected component identity is important for this, okay? Because I'm going to be looking at orbits of things under this, right? And if I allow the whole thing, it's going to be different. Okay. And so now what should I say about this SL2 orbit theorem of, in this case it's just one variable, so it's Schmidt. So what is an SL2 orbit? So this is a map theta from the upper half plane into the classifying space D, which is holomorphic. It's horizontal, it satisfies Griffith's horizontality, and 2, there exists a representation rho from SL2R into GR such that theta of G acting on the square root of -1 is equal to rho of G acting on theta square root of -1. So this really is saying that this comes from some equivariant embedding, okay, about the SL2R. This is what it is. And so in this case, we let T be rho of 1, 1, 0, 1, and our monodromy logarithm N is log of T. And then I will write F, this is the limit Hodge filtration F, this is e to the minus square root of -1 in theta of square root of -1. And eventually if theta, square root of -1 is going to become I. But maybe to make sure it is clear on the chalkboard, I try to use square root.
Before you erase this theorem you're erasing right now?
Yeah.
The S, must it be dimension 2?
Yeah, it's two-dimensional. Yeah, I'm sorry, it's two-dimensional. Yes. Dim S equals 2. So that's, yeah. Okay, so ALMA has a very specific period map. So that's, okay, so this is the kind of, okay, I was going to talk about this later, but I'll talk about this now. No, it's good to talk about it now. So the problem with the classical theory for like Shimura domains, right, is there's kind of like a universal variation of Hodge structures. So you're really compactifying the universal object. So the kind of moral of the story, at least from this theory, right, is that if you want to do it for a particular period map, then you have to take those particular monodromy matrices and you have to use that one to construct a fan which will compactify that particular period map. And it will not, in fact, they made a bunch of conjectures about the Kato Nakayamsui made a bunch of conjectures about the existence of complete fans. And actually, let me strike Nakayama for that, because it was a Sui student in his thesis that proved that you couldn't do that. Okay, so kind of a complete fan, like that's just not going to happen. Okay, so now I want to prove a little lemma. Actually, I'm not going to prove it. Let me just state it. Okay. So this is a lemma that says the naive limit Hodge filtration let me call it F sharp is the limit as y goes to infinity of theta of y square root minus 1 exists and belongs to the topological boundary of D inside of D check. So the picture for this so here is when the Hodge numbers are 1, 1, which is the only case I can really draw. So the compact dual D check is P1. And now we have a natural action of SL2R on all of this, yes? So one orbit is the upper half plane. That will be D. Then we would, of course, have U bar, if you'd like, D bar, and then, of course, we have S1 here. So we have P1 is an orbit, union of GR orbits. And for any period domain, I'll be able to play the same game, except that union of boundary components is going to become very complicated very quickly. Okay? All right. And so maybe complement the earlier lecture. So this Nilpolt-Norbert theorem, what it's saying is more or less on the upper half plane, this period map looks like f of z is e to the zn, e to the gamma of s on some limit Hodge filtration, where here, this is a covering map, right? We have u down to the punctured disk by s is e to the 2 pi I z. And so this gamma of s is an analytic function. And then, of course, I guess there's an exponential coming here. So this is what maybe, well, ask Zimmerman about this. I think this maybe complements a little bit about what he was saying earlier. Okay. And now the SL2 orbit theorem, among other things, what it gives you is, one, it tells you if you take this limit Hodge filtration, which is not F sharp, and you pair it with this object called the monodromy wave filtration with some appropriate shift, this is a mixed Hodge structure in the sense of Deligne. And another thing that it gives you, which is related to what I had written on the board earlier, is this gives you a bunch of norm estimates. Okay, so maybe that's a small repeating what was said in the earlier lecture in a slightly different fashion. And so now what am I going to do? So I'm going to let psi of d equal SL2 orbits theta from, no, I had that right, from UN to D modulo the action of SL2R. So now let's see what happens. So if I take this Nilpolt-Norbert theta of z is e to the z in f, and I take some element little g in gr, then what happens? So g theta of z is g e to the z in f is g e to the z in g inverse g f is exp at g, and I guess I put a z in front of it, in gf. Yes, this is exactly what happens. So what I should do then is I should Oh, and let me do that also while I'm saying it. Okay, so also obviously limit as y goes to infinity of g theta of iy is g limit y goes to infinity of theta of iy. So what are we going to do then? So we're going to let nilp of gr equal nilpotent elements in gr modulo the adjoint action of gr, and we're going to let delta equal gr orbits in d bar is d union its boundary. Okay, so what do we get out of all of that? Well, we get a nice, so we have psi d here. Then obviously it maps down to, oh, I forgot to give this a name. Oh, I gave it a name there. Okay. This maps down to nilp of gr, and it maps down to delta, clearly. Yes, so the map here is theta goes to n, and the map here is theta goes to f sharp. Okay, so we have two maps like that. Okay, so now, of course, I'm really only interested in the images of these maps. So this will be nilp d of gr and delta of d to indicate the things that could actually come from the image of this map. And so here we have a natural, okay, so here we have a partial order by n1 is less than or equal to n2 if n1 is contained in the analytic closure of n2. This is analytic closure. This is a real object, real analytic closure. And now here we have the same thing for orbit closure, right? So but the one thing here is this actually gets reversed. So O1 is, less than or equal to. O2 means that the orbit closure of O2 is contained in O1. Okay, so, but these are both partial orders. And so this theorem that I proved with Matt and Colleen says that it says that there exists a reflexive anti-symmetric relation on psi d, which is compatible with that diagram star that I just drew. So if two things are related in here, then they're related in here, and they're related in here. Okay. So, close up?
What does antisymmetric mean?
So A less than or equal to B, B less than or equal to A implies A equals B. So if I were to add transitive to this, then it is a partial order, yes? And now, this is inclusion. Inclusion is, or reverse inclusion, those are partial orders, right? Okay. Okay, so now you should ask me, well, Greg, can you give me some examples of this? Okay, so So the simplest one would be, for curves, this ordering is, here's the smooth curve of genus G. Here's one node, and here's two nodes, okay? So it's the obvious ordering, right? And what I want you to see from this is that this is clearly, not that this is partially ordered, this is linearly ordered, right? And so that's another theorem in this paper, is that D Hermitian symmetric implies psi D is linearly ordered. Okay. So okay, there's a lot that's written on this board. Most of it's not important, which is why I wrote it up on the board, so I didn't have to waste any time doing this. So, okay, so if you take this D, which parameterizes these 1, 1, 1, 2 things, then this relation, so this period domain is not Hermitian symmetric, and one checks by looking at the possible limit mixed Hot structures that can come out of this, that indeed it is not transitive. Okay, so in this case, you do not get a partial order. And I would also point out that Ding's example, it actually is a partial order. So this is more, this is not a conjecture, it's not a remark, it is more like a fever dream or something like that. But as it stands now, I mean, at least by pure algebra, I think it's probably very hard to construct a fan in the case where this relation is not a partial order, because at some point you're going to have to subdivide these fans, right? And if you don't have any type of ordering on like the set of nilpool Norberts, I think you're going to like get stuck somewhere, right? You're not going to know what to do. Maybe by pure geometry you can do it, because I mean the monodrome of an actual family of smooth projective varieties is super, super rigid and restrictive. And so maybe by some high-powered geometry you could do it. And the next one, that I need to erase something, maybe I erase that. Okay. So, okay, so this will be the main kind of object that I'm going to talk about. This next example will be when D corresponds to Hodge structures of type 2, M2, where M is greater than or equal to 4. And so in this case, what this relation looks like is this. I'm not going to draw you all of the mixed Hodge structures for this, but in this case, this 2M2 case, okay, it's not a linear order, but at least it's a partial order. Okay, so it's a reasonable thing. And the other reason that like these types of examples are reasonable is because we mentioned Griffith's horizontality. Or infinitesimal period relation. So for these types of period domains, this horizontal distribution inside the tangent distribution, this is co-rank 1. So it's not Hermitian symmetric, it's not completely integrable, but it's as close as it could be. And now, by the way, I mean, as soon as it's not integrable, the dimension of the maximal integral submanifolds can drop by a lot. It's not that it's co-rank 1, so the maximal possible things are divisors. I mean, that's just not true. Okay. So any questions on this? Because now I'm going to start like the thing that I advertised in my abstract. But I wanted to at least give like some idea of like where things were coming from. So no questions. Okay, so the first thing that I want to say about this You know, I'm going to leave this here because somebody's going to ask me some question about this at the end of the talk. And then I'm going to be stuck that I erased it, right? Okay, so let's not erase that. Oh, and now I need to put the corner of death here, right? Yes. Okay. Yeah. Okay. So, so this is like part 3, I guess. So this is moduli spaces of Water-Gamma surfaces. Okay. So, I'm not even going to write this on the board. If you're an algebraic geometry, I am thinking about smooth, projective, connected, minimal surfaces of general type with complex numbers with ks squared equals 1, geometric genus 2, and irregularity 0. I suspect for many non-experts, a better way of saying this is these are degree 10 hypersurfaces in P1125. Now, if you haven't seen this before,
Weighted projective.
it's a weighted projective space, right? So we have a C-star action, and the usual projective space has all weights 1. You can add different indices there. Okay, so this is maybe a much more concrete way of expressing this thing than what I just said about minimal surfaces. Okay. Okay, so now the first thing you could ask me is, what are the Hodge numbers for this? And the Hodge numbers for this are 2, 28, and 2. So this is not a Hermitian symmetric domain. And the next thing you could ask me is, well, Greg, what is the dimension of this moduli space? And the answer to that is 28. Okay, so now why would you want to study this? Again, so the thing for the experts in algebraic geometry, they probably already know this, but there's this basic Noether inequality in the theory of surfaces, and these are like an edge case for the Noether inequality. So it's a very natural case to study in the geography of algebraic surfaces. I told you it has corank 1. That's another reason to study this. It's as close as I can get to being integrable without being integrable.
You mean the period domain is dimension 29?
Oh, this is primitive. Yes. And if you don't, yeah, it's 29 if you think not primitive, but yeah, primitive it's 28. Yes.
No, but I'm just saying there's a moduli space and it sits to the period domain.
Yes.
And are they just different, right? Because not dimension symmetric.
Yes. So the period domain has dimension 56.
Oh.
The period domain has dimension 56. This particular moduli space has dimension 28, and that is actually equal to the maximum possible dimension of an abelian subalgebra of GR. So you cannot do any better than this. Okay? Yeah? Question? Okay.
But is there, okay, so maybe this, like, is there a relation between 28 and dimension 1 space and 28 and just H11?
Well, as was discussed in the previous lecture, I mean, would you calculate the dimension of this thing? Well, you'd have to go through this Kiranishi space and write everything in terms of cohomology. And I mean, yes. I mean, the short answer to that is yes, but I don't want to.
So it's unobstructed.
It's unobstructed, yes. Yes. Now, if you're not an expert, the easy way to do this is just count the number of polynomials of degree 10 in that weighted projective space and calculate the dimension of the automorphism group of that weighted projective space and subtract. That would be the easier way to do that. But you could also do it the way that you're suggesting, yes? Okay. Let me skip that. Okay, so now, how am I doing for time? Okay. So, I guess 4. This would be boundary divisors of M contained in M bar. And now the first thing that I would like to say about this, maybe I'll say it this way. So this is a KSBA moduli space. So this targets semi-log canonical singularities, okay? And the only thing that I'm going to tell you about that is ADE is canonical. So ADE singularities are beautiful singularities. They're a wonderful class of examples. As far as this moduli space is concerned, they're in the interior. They are not in the boundary. Okay, okay, so now what am I going to try and do? So the title had unimodal. Okay, so for complex, in Arnold's classification of isolated surface singularities, there's a bunch of invariants, one of which is the Milnor number, and one of which is the modality. Okay, did this thing go off? No. So modality 0 is ADE, and the E here is E6, E7.
Sorry, I think your microphone died?
Yeah, well, I mean, the microphone, I can try resetting it, but. So modality 0 is ADE, and so A and D, there are an infinite list of them, but E, there are only 3 of them, yes? Okay, so the next thing is modality 1, and so here there are a bunch of triangle inequalities. So they correspond to x to the p plus y to the q plus z to the r equals 0 with 1 over p plus 1 over q plus 1 over r less than 1. There are infinitely many of these. And then there are 14 exceptions. And the thing I need what's under that board there, so I'm not going to move it. So what we can do is we can think about these things for the moment. Oh, there's another thing I should say. Okay, so let me think about P1, 1, 2 for the moment. So this will have variables x, y, and z, and variables 1, 1, and 1, 2 is 1, 1, and 2. So this does not work for most weighted projective spaces. But whenever you have a 1, you can get a nice ordinary coordinate patch by, in this case, the trick would be u would be y over x, v would be z over x squared, where x is not equal to that. Now, if you have other ways, that won't work. But when the degree is 1, this gives you a nice coordinate patch. Okay, so now I can really think of some polynomial p of uv, which has an isolated singularity at 0. At 0, modality is equal to 1. Okay, and so there's 14 of them in Arnold's list. Now I could ask, which ones will I be able to represent using a homogeneous polynomial of degree 10 in P1125? Okay, so the 5 variables are always a double covering variable, so it's really just for P112. And you just look at his table, and you will discover what the answer is. Okay, so again, this table is not important unless you're actually doing the calculations. Okay, so for W12, PQ are 4 and 5, D is 20. So I will look at x to the a, y to the b, z to the c, so that a plus b plus 2c is equal to 10. So it is actually homogeneous to degree 10. And then the other thing I'm going to define the weight of this guy here to be p times b plus q times c, p times c minus d, where these are these numbers here. So for W12, the weight is 4 times b plus 5 times c minus 20. All right, and so what do I want? Well, after I do this, you see that x is not in that list there, right? After I do this game, I want polynomials such that look at all the monomials that occur. That weight function is weight greater than or equal to 0. If I take a polynomial with that property, then it will have an isolated singularity at what will be in these coordinates 1, 0, 0 of that type. And the W12, W13, that's the Milnor number of the singularity. But that's maybe not so critical. So the point is, we get a bunch of singularities from Arnold's list, and so what I'm claiming is that I can build a bunch of boundary components, in this case, via moduli space, using these things. That's what I'm going to show. Okay, so now I should make some remarks. So I guess I should make a remark. So, Franchosi, Ardini, Rana, and Rolinski found 3 other boundary divisors. They found 3 boundary divisors in bar, but those are distinct from Mars. So I don't want to say that like I'm the one to find these things. Okay, there are some other ones that were already existing, but they're of a different nature than what I'm going to discuss here. I have written the table. Now another quick calculation. So for each of these singularities, you go through, you ask your computer to do this for you to make sure you don't mess up. There exist exactly 2 monomials M1 and M2 such that the weight of MJ is equal. There's always 2 of them. So now to make my calculations with various automorphism groups easier, which I'm not going to do that in the short amount of time that I have left, but when I'm doing the paper, we are going to pass to the subspace where the coefficients of these 2 monomials are equal. If you don't have to do that, you just have to work more with the automorphism group, or you can just say I scale that away and be done with it once as well. Okay. So that's just a silly calculation. Save this for the question somebody's probably going to ask me at the end. Okay, so what's up now? So definition, U is equal to F in C of X, Y, Z, such that degree of F is 10, and the coefficient of M1 is equal to the coefficient of M2. And then, I mean, in an obvious way, we have U plus U0 and U minus contained in U given by the weight function, right, of the monomials. And of course, I have pi plus pi 0 pi minus the obvious projection operators from u onto plus u0 minus. Okay. And now, so the regular locus of some subspace u contained in w contained in u, this is w minus pi 0 inverse of 0 intersect w. So the regular locus means the coefficient of that, like m1 plus m2, is not 0. And so then it's easy to check that if I take, okay, so this u I'm supposed to view as the space of coefficients for my polynomials, right? These are my polynomials. So the regular locus of this, which means the projectivization of u reg, this is easily seen to be isomorphic to the projectivization of u plus u0 reg cross p of u0 plus u minus reg. And now you understand why I wanted to scale that coefficient to be 0, because now if I want to take those two things in these pieces here and here and patch them up into something in the bigger space, yes, I just rescale them so that the coefficient of like that m1 plus m2, 1, so they're the same, and then I just glue them together. So that's the reason for that little condition. And now, I can also define a natural C star action. And so this is just T star of monomial M is equal to T to the minus weight of M if the weight of M is less than or equal to 0, and times M, of course, and M if the weight of M is greater than 0. Okay, so this C star action on the u0 plus u plus, which corresponds to the surfaces which are going to have this orbital singularity of fixed type at the point 1, 1, 0, on those, I act trivially. On the rest, which is going to be called the tail, I actually act in some non-trivial way. Okay. Okay, and so why did I introduce this whole thing? So, so for generic u in u reg, if I let S be w squared minus T star u equals 0 in 1, 1, 2, 5 cross C. Oh, so now you're going to complain about I put C there and not C star. Okay, this action is also built so that it extends actually to an action of C, right? Okay. This S here, so this is a and then I let S0 be okay. So this is S. We have a morphism from S down to C, and of course we have S0 is pi inverse of 0. So this whole thing will have the property that I think I said generic already, but for generic case, S of t is pi inverse of t is smooth, pi sub 0 has exactly one singular point at 1, 0, 0, 0. Okay. And so now what can we do? So I can let z be equal to the variety defined by pi plus of u plus pi 0 of u, or I guess I should say equals w squared, since this is in P112. Or if you'd like, I mean, this is literally the limit as t goes to 0 of w squared is t star u. Because that's what happens, right? This action was set up so it killed off everything in negative weight. So it's the limit. Okay, so now I'm going to have to define z tilde, so this will equal the pq weighted blow up of z at this singular point. I'm not going to define weighted blow up, but it's exactly like an ordinary blow up with some different coefficients. Okay, and p and q is really like that p and q. But I already put that on the table. And so now, the next part of the construction bifurcates in the case where d is even or odd, so I'm going to let d be even. Otherwise, there's a way of rehomogenizing the weights that's well known to experts and not terribly interesting to do in this case. So what do I do for y tilde? So y tilde will be the variety defined by, I need a new variable, v of omega squared minus sigma. I guess I put v there, then I don't need equals 0. So what is this? So this is in P1, PQ, d over 2. This is my variable omega. And how do I get sigma? So for sigma, I take t star of pi 0 of u plus pi minus of u, and I evaluate it at x equals 1. So now it has t. If I got rid of the x, it still has y and z. And so now the degree of y will equal p, and the degree of z will equal q, and the degree of t will equal 1. And you will now notice that this weight function was exactly tailor-made to make sure that this will give me an ADE K3 surface in this weighted projective space, right? Okay, so this will give me y tilde is an ADE K3. And so now I have to tell you what I'm going to do to build my, I say the main theorem, and then it'll be time to talk. Okay, so it actually might have worked this time. Okay, so okay, so the main theorem is that each Arnold singularity type sigma on that list of A1s, there is a corresponding divisor d sigma parameterizing generic surfaces which look like this. This is PQ. This is Z tilde. This is Y tilde. And now I should tell you how I glue them together. So, okay. So for Z tilde, the PQ, this comes from the weighted blow-up. You do an ordinate blow-up, you add in a P1. You do a weighted blow-up, you add in a PQ. That's just the way that works. And so this thing always has two singular points. Now, to rigidify gluing one of these P1s, you need 3 ones. And so, again, this is some algebraic geometry lingo. You have to look at the strict transform of the branch curve downstairs, and that will give you the extra point that you need upstairs to get 3. And it depends on the case. I mean, sometimes it can go through one of the other singular points, but the point is you always get exactly 3 altogether when you take the 2 singular points plus the strict transform. Okay. And now for this one here, you could set t equals 0, you could set omega equal to 0, and now you've again got this PQ sitting inside of it, and now you could look at where this other branch curve intersects, and it will also give you exactly 3 points once you do all the calculations. And so now you have 3 points, 3 marked points on this P1, and now you know exactly how you should glue these two surfaces together. And I think that I will not have time to talk about this, and that's okay. So the next thing you're going to ask me is, Greg, well, what's the monodromy representation of these things? And in this particular case, it turns out that these degenerations all have finite monodromy, and the reason for this is that it turns out that this surface Z tilde, its geometric genus is equal to 1. And so there's using this Clement-Schmidt sequence, that I'm certainly not going to talk about, you can kind of prove the following. So the geometric genus of the generic fiber is, after you go to some semi-stable generation, is always greater than or equal to the sum of the geometric genera of the components. And if that's the actual equality, then you have finite monodromy. And so in this case, Z tilde has geometric genus 1, and ADK3 surface has geometric genus 1. So in that case, there's finite monodromy. And then by an old theorem of Griffiths, this will tell you that the period map, on a small disk from delta star into D mod gamma, this will actually extend to the full disk into D mod gamma. So I think that is probably a good stopping point, because I think I have just about used up my time.
Any questions or comments?
Can I ask like a big picture question?
Yes.
So you described for us, in this case, these sort of divisors that you're
Yes.
identifying some of the behavior. If you look at the period map for these spaces,
Yeah.
does what you do relate to?
Oh, this is excellent. I forgot to say this. Yeah. Thank you for asking this question. So one thing I should have said, I forgot to say this. So another reason to study these things is that not only do I have this nice partial order diagram, right, but Franciosi, Bardini, Ron, and Walensky, they actually put together like various papers that they have. So in this case, every single limit mixed Hodge structure which should appear Hodge theoretically, it's actually realized geometrically in this modular space. Yes, so we have not constructed a fan for this. I do not claim this in any way, shape, or form. But I mean, so this would be like, you know, this kind of, I mean, this is somehow like probably the most accessible example on the Hermitian symmetric case for these types of.
But does it give you a compactification for the period image? Or just partial compactification along these divisors? Or is that a different issue altogether?
If you give me a curve that somehow only manages to go through these types of things, then of course it will, by Griffith's thing, give me a compactification,
Well,
right?
it must be a curve. It can't be a surface, for example.
Okay, you could even, okay, yes, I mean, so, but,
I know that's rare, but let's say magically I gave you a surface which has those properties.
okay, but what did I say? I mean, what I really prove here, right? I mean, this is all about generic, right? So I don't know, I mean, the two-dimensional thing, I mean, these divisors could be intersecting, right? And there could be some places where, like, the generic thing has finite monotomy. That doesn't mean that if I generated even more, that it could have infinite monotomy, right? So, I mean, and that, having proven this, I mean, the rough idea for that would probably be that modality 1 and modality 1 probably intersect in something that either has two singularities in modality 1 or like a singularity in modality 0. That would be an obvious conjecture. I mean, it's not proven. But let's see, what can I say for that very quickly? So at least for the Z and W's, you can prove that they are birational to a K3 surface. Now this birational involves removing something that goes to the singular point, okay? So take this with a grain of salt, but for Z11, it's a double cover of a smooth sextic, but there's a special line which intersects in multiplicity 1, 2, and 3. Usually Pazoo would say, well, you get 6, but they're distinct, right? This is, and W12 is a sextic, and the line has multiplicities 2 and 4. So, yeah, so that's a good question.
More comments, questions? If not, let's thank Greg.